right, welcome back. Remember that we are live on Piazza and YouTube if you have any questions or you want to have a discussion with other students in the class. But otherwise, what I wanted to do is I wanted to provide an end cap to your lab yesterday, where we already exposed you to to using a non-interactive input, the command line arguments, basically. And what I wanted to do to end the first module here is to go back to our original kilometers to miles program, and let's go ahead and modify it so that it is using the command line arguments instead. Remember that it works like this. I need to be in the correct directory. Let's see. All right, GCC, kilometers to miles, and when I run it interactively, it asks me to enter the miles, so 10 miles, say, which is roughly equal to 16K. What I want to do is I want to take that file and I want to change it to a command line argument version, kind of like you did yesterday in your lab. The vast majority of people got it. So we'll go ahead and just reiterate for those that may not have been able to finish it up last time or in their lab yesterday. What I'm going to do is I'm going to copy the file over. CP is short for copy. So I'm going to copy the file KMS to miles to another file called KMS to miles command line argument, CLA for short. All right? And you can see over here that this new file has been created. Now I'm going to go ahead and start editing that file. So instead of prompting the user for input, what I'm going to do is I'm going to assume that they've given me a single command line argument as the miles. Right? And so miles is equal to argv sub. Now, which index do I use, or which value do I use for the first user-provided command line argument? 1. All right. Now, is that going to work? Let's find out. Let's find out what happens when I try to compile it like this. KMS to miles, but I want the CLA instead. Right? It's going to complain about this. Error, incompatible types. Assigning double to type char star. We don't know what char star is yet. That is basically a string. So what was my error here? Yeah, go ahead. Yeah, I need to convert it from an alphanumeric character string into a number. Now, do I want integers, I, A to I, or do I want floating point numbers, A to F? F, okay, because miles is a double, A to F. Right, and they might, I've only been testing it with whole numbers, 10, 20, whatever. But of course, you can allow a user to put in 10.5 miles and convert that to some kilometers. Right? Okay, what else? I don't need the scanf anymore. It replaces that entire prompt read process. So let's try this again. Right, and it compiles this time. And let's run it. I'll give it 10 miles, 10.5 miles just to make sure that it works, which should be slightly more than 16 kilometers. And it is. Looks like it works to me. But let's try to break it. First of all, should I be allowed to put in negative 10.5 kilometers? I don't know. Maybe. If you want to, if I run backwards, I'll run backwards 10.5 kilometers or miles. I want to know how much I ran backwards or something like that. Force can be positive and negative. Charge can be positive, negative. Depends on your perspective, right? So maybe negative values are allowed. Maybe we want to design our program so that negative values are not allowed. All right, so that's probably one bad input that if we make the design decision that we're not going to allow negative inputs, then that's one thing that we need to take care of. What's another, this is what you were asked in your lab to identify. What are some bad inputs for dates? February 20, well, not February 29th because it could be a leap year, but February 31st, right? That doesn't work. Right? What happens, right? Say what? Libraries? Letters. Oh, letters, okay. Let's find out what happens here. TEN? What's going to happen here? What do you think? 0 to 0. Okay. Is that expected? I didn't put in 0. I put in TEN. You should be able to read my English and convert that to a number, right? No, it's not that sophisticated. What actually happened here under the hood was it says A to F, or yeah, A to F. We told it to parse this as a number, TEN. And so the first time that it sees something that's not a number, not a digit, t, it says, okay, well, I must be done. What have I parsed so far? Nothing. What's the numerical value of nothing? 0. So here you go, 0 converted to 0. So that might be something else that we want to take care of. What's yet another thing that we may want to account for? What if they didn't provide any command line arguments at all? What do you think is going to happen here when I hit this enter button? Some error, segmentation fault. What the heck does that mean? Well, I'll give you a preview later on when we do memory management. Memory is divided up into segments and pages. A segmentation fault is when you try to access an area of memory that doesn't belong to you. And so it faults you out. You can't do that because that would be a severe security risk, right? Being able to access any old part of the memory. I could access another program, another user's program that's running on the server. No, all right? So segmentation fault, okay? So let's take care of that first, this last one now. We expect one command line argument, or how many command line arguments do we actually expect here? One user command line argument, but remember, what is the first command line argument? argvis of 0. That's always the executable file name. So in this case, we are actually expecting 2 command line arguments. If we don't get exactly two command line arguments, the executable file name and the 10.0 that we expect, then we should give them a proper error message, not a segmentation fault. We should say, you need to provide the number of miles, okay? So to do that, we need conditionals. And I'll show you really quick here how to take care of that. If the number of command line arguments, argc, C stands for count, is not equal to 2, we're going to go ahead and print an error message. Error, you need to provide miles, right? And then I'll exit on them, right? Now don't worry about the syntax yet, that's what we're about to get into. But now I can show you that it is a much better behavior, at least for that last case that we took care of here, right? Error, you need to provide minutes. Oh, okay, now I know what I'm doing. So 10.5. There we go. Okay. So to do that, we need conditionals. That if statement that I just made is it's called a conditional. Right? I'll go this button. Okay. And that starts us in on our next module. Now, on Monday, we will not have class, of course, because that is Labor Day. But on Tuesday, you will have your first lab on conditionals. So we'll cover just enough to get through that first lab. Normally, programs have sequential control flow. If you have statements A, B, C, then they are executed A, then B, then C. They're not executed in some random order. More complex problems, however, require that you make decisions. Okay, well, I'm at a point now. Do I do this thing or do I do this thing, depending on somebody's age, right? If you're 18, oh, you're technically an adult, so you can go ahead and sign this contract. No, you're not 18. Sorry, you can't do that, right? Conditionals are how you specify one or more conditions so that one piece of code will execute or a different piece of code will execute. Or one piece of code will execute or not at all, right? We'll skip that piece of code so that you have condition, if you have statement A, B, and C, but B is conditional, we'll execute statement A. If the condition is true, then we'll execute B. If it's not true, we'll skip B and go on to C. You can specify that under some condition, or maybe even a third piece of code. You can do one piece of code, 2 pieces of code, 3 pieces of code, as many as you want. The way that you achieve this is through a bunch of if statements, as I already demonstrated here. If the number of command line arguments is not equal to 2, then we go ahead and error out and quit on them with an error message. Okay? You can also have if else. That allows you to do 2 things. If the condition, then you do A. Otherwise, you do B. Else, you do B. You can also have multiple conditions. If A, then do this. If B, then do this. If C, then do this. And as many times as you want. And those are if-else-if statements. Conditions rely on some sort of a logical statement. And this might be your first introduction to Boolean logic, where everything, a Boolean statement is either true or false. It's not anywhere in between, right? That's not what we're looking at. That's not, it's half true, right? We're not looking at weasel statements like that. We're looking at pure Boolean logic. It's either true or false, right? You might not know what the condition is, and certainly when you code something, you don't know up front what the condition is. If you did, why are you coding the condition? If this condition is true, then you just always true, then you just write code that executes. If it's always false, don't write code at all, right? So you don't know up front what the condition is, but when it executes, it is either true or false. Right? So let's start looking at, hopefully the live stream looks to be good. But again, remember, we are online, so if anything goes wrong online, let me know about it, and I'll see what I can do. Right? Not much I can do because my computer overheats, it's too old, and I lost my D button, or D key today. So I'll try to find words that don't have a D in it instead. So basic syntax. We're just going to jump right into it here and start doing some examples. Now, these are not real statements here. I'm going to use placeholder values until we get into the actual logic statements. So here is an if statement, and it uses, surprisingly enough, the keyword if, right? Now, I'm putting parentheses here to put in the condition. This is not a real condition. Condition, there's my first D, right? I put in a condition here. That condition is either true or false. This is not real syntax here, okay? That's just a placeholder, and then we'll talk about what type of conditions you can set later on. Then I've got an opening curly bracket and a closing curly bracket. The opening curly bracket and the closing curly bracket will encompass any code that you want to execute if that condition is true. So I'll put that into comments. So if the condition is true or evaluates to true, then anything inside this code block will get executed. If the condition is false, this code block will not be executed at all. At all. Okay? I can put whatever I want in there. Okay? Let me go ahead and copy. Oops. No, what? No, we don't have any conditions yet, so let's go ahead and go with the rest of the syntax here. Now, alternatively, you can have an if-else statement. So all I'm doing is taking the if statement and then tacking on an else statement afterwards. So if, and then again, condition. And again, that's just a placeholder. That's not a real piece of C code right there. If condition, so statement A, right? Else statement B, right? Now, how does this work? In this particular example, let me go ahead and go back out of code mode here, on if-else statement, right? And let's go ahead and note some things about how it works here. So if the condition evaluates to true, I'll fix my spelling later, then statement A is executed. If the condition evaluates to false, statement B is executed. We say that these are mutually exclusive. The two statements are mutually exclusive. What does mutually exclusive mean? It means that they exclude each other. They are mutual to each other. That if statement A executes, you know that statement B will not execute. If statement B executes, then you know that statement A didn't execute. It's one or the other, not both, and not neither, right? So sorry for that double negative there, but exactly one of these statements will execute. If the condition is true, then it executes that first code block, whatever is in that code block. It can be multiple statements. Otherwise, it will execute the second code block, where statement B is located. Now, I didn't provide a condition on the else statement, right? Because of Boolean logic, a condition is either true or false. I don't need, if it's true, then that executes. If it's false, then this executes. I don't need a second condition to tell me that it's false. It's the same condition. It's just flipped, true or false, right? Now, you can expand this to any number of conditions. An if, else if statement. Let me go down, statement. Let me go ahead and write it first. And for this, I'm going to do, I'm just going to steal my code from up here and modify it. Right? Here I do need to provide more than one condition. Else if the second condition. Condition 2. I'll name them 1 and 2. Then statement B, else statement C. Right? So in this case, and then let's mark this up as C code. There we go. Now it's nice and pretty. So here I've got 3 different statements. It's going to go in order. If the first condition, condition 1, is true, then statement A will execute. If it's false, it moves on to the next possible condition, and it looks at condition 2. If that's true, then statement B executes. If it's false, then it moves on yet again. You can string as many of these together as you want. You can have if condition 1, else if condition 2, else if condition 3, else if condition 4. The else statement down here is basically a catch-all. If none of those conditions were evaluated to true up there, then it falls through basically, and statement C is evaluated. And not only that, but the else statement is optional. Why? It was optional up here. We didn't have an else statement here either. So if you want to, you don't have to have an else statement down here. Right? So some notes on this. The first condition to true is the only one whose code will execute. Right? So you do have to be a little bit judicious about your statements. In general, what you want is the most specific, then leading down to the most general down here. And we'll see a couple of examples of that as we move along here. But otherwise, all conditions are mutually exclusive, and the else block is optional. That's the only difference between an if statement and an else if statement. The else statement is optional. If you don't want it, if you don't have alternative code, then you don't write it. Now, plenty of new folks, they write it no matter what. If statement A, then do this, else, and then they'll leave a blank code block. Don't do that. That's bad style, right? So, style tip. Do not leave blank code blocks. Rethink your logic, right? So rearrange your logic. If you have a blank code block, especially in an else statement you could just go ahead and get rid of it. But if you have a blank code block in an if statement, then rethink what you're doing. Reorganize your logic so that you don't have blank code, right? Blank code is dead code is bad code, right? All right. So order is important here. You generally put the most specific conditions first, then the most general last. And because, of course, they are mutually exclusive, then the first one to get executed, that's the only one that gets executed. Okay? All right. So let's go ahead and go with a couple of demonstrations here. So let's go ahead and copy the hello world into a demo file, demo.c. And let's open that up. And blank slate here, let me just go ahead and give myself a program to start working with. Okay? So let's go ahead and predict the Husker scores on Saturday. And of course, they're going to be integers because you can't have 3.5 points in a football game. So Husker score. Anybody know the over-under? I think that the spread was something ridiculous, like 40 points, but I'll still take I'll still take him to cover. All right, no gamblers out there. That's all right. Don't gamble. It's bad. All right. Husker score. Anybody want to guess? Oh, let's go with 50. Okay. All right. Fullerton, is it? Or Fulton? Fordham. That's it. Fordham score. What do you think they'll get? The D looked okay. 14. All right. There we go. Give them another. They got within 30 yards or something. All right. Okay. So we can change the scores later on. The scores don't really matter. What we want to do is we want to determine who won. All right. So if the Husker score is less than the Fordham score, who won? Printf, Fordham won. Yay. There we go. So what is this going to actually print now? Who won? Huskers won, so it's not going to print the Fordham one, right? Just with the code that I have so far. Because I just had an if statement here. Okay? The Husker score was not less than the Fordham score. So it ended up skipping this statement entirely and moving on, and then ending the program. So we want more outcomes here. So let's put an else statement here. Else printf Huskers won. Yay. Okay. Let's try that again and run that. Huskers won. Now it actually prints something. Is there any other outcome? For a soccer game, there'd be another outcome, but no, football doesn't have that outcome. Proper football doesn't have that outcome, right? So, so else if, let's put this condition in here. If the Husker score is greater than the Fordham score, then the Huskers won, right? Is there not any other condition? But assume that just 4 quarters. It could be a tie. All right. Printf tie for now. Let's go to overtime. Right. And unfortunately, that's on BTN, and I don't get it, so I'm going to have to go somewhere and watch it or something. I don't know. If anybody wants to help me out and find out how to pirate BTN, let me know. Anyway, let's go ahead and change the scores so that it's actually a tie. Oops, I don't want to go all that way. Let's go ahead and suppose that it's a tie. All right, GCC and run it. And now we're going to go to overtime. Okay. So there's an example of if, and else all together, right? Now, these weren't more specific and more general, but I do need a second condition. If I've got 3 things to choose from, I need at least 2 statements. I need 2 conditions. If I had 10 possible outcomes, I would need at least 9 conditions, right? And hidden in here is our first piece of logic, where we can take numbers and compare them to other numbers, where we can take variables and compare them to other variables, or take variables and compare them to other numbers, just using the symbols that you're already familiar with. All right? So let's talk about some numerical comparisons. Conditions. Numerical comparisons. Sons. There we go. Ignore that. All right. So you can compare 2 numerical values. All right. No, there we go. It didn't freeze. They can be both variables or literal values, or a mixture of them, or even expressions. Right? So we'll get to a couple of examples here in a moment. But otherwise, what have we already seen? Less than. Right? This is strictly less than. How do you think that we get less than or equal to? Do you see that? Oh, now in math, you would write it as less than or equal to with this bar under it, right? But you don't see that anywhere on your standard QWERTY keyboard. So our approximation here is going to be how we read it. Is it less than or equal to? Right? So less than or equal to. Right? And likewise, you can go the other way. Greater than, strictly greater than. Or, and the way that you read it is greater than or equal to. Greater than or equal to. Right. What else? If you want strict equality, you can use equals equals. Why can't we just use a single equal sign? That already has a meaning, right? Well, yeah, what is it for? Assignment operator. So, because we made that mistake of using the single equals operator for the assignment operator, we're forced to use another equal sign. By the way, there are some languages that are dynamically typed where you can have even, this would be what's called loose comparison operators. If you want an even stronger comparison, just add another one, right? And then equals equals equals. JavaScript, PHP, and a couple of other languages like that support that, but not C. Right? Don't write that in C. This is equals. Right? And it's going to evaluate to true if the thing on the left-hand side and the thing on the right-hand side have the same value. Right? How do you negate this? Well, if you were to write this out in math, of course, you would put an equal sign with a slash through it. We don't have that on our standard QWERTY keyboard. So the best approximation that we have is an exclamation point, which kind of looks like that slash, and then the equals. Yeah, you could have. They could have used maybe a backslash or a forward slash, or maybe even that what's called a Sheffer stroke. Right, this thing right here. Sometimes we call it a pipe. Right, it's piping things, but that's not what they use. Those have other meanings into other contexts. Okay. So we're left with not equals, using an exclamation point and an equal sign. So not equals. Right? All of these operators only operate on two operands. And that's going to be important later on when we start looking at some pitfalls. You cannot have, you cannot string them together and expect it to work. Okay? All values must be numerical. Right? If they're not numerical, if I try to compare like a string, hello, to goodbye, it's not going to work. There are going to be warnings. It'll probably run, but it will not give you what you're expecting. We'll talk about how to do that with strings later on. Operands. So when you've got operators, right, like plus, minus, all that stuff, like A plus B. A and B are the operands that the operator operates on. In this case, if I have something like, I'll just go into code mode really quick here, and if I've got something like A equals equals B, right, then the equals equals is the operator, A and B are the operands, okay? So we'll come back to that here. Operands can be variables, literals, that is, actual numbers, or expressions. All right. Let me get rid of this. There we go. Hopefully that stops the error messages I'm getting. All right. So let's go ahead and try some things out. All right. We'll forget about the Husker score right now. And let's go ahead and just go with a few other values here. 5, int b is equal to 10, int c is equal to 15. Right? What's the result going to be here if a is equal to 0? Right? Is that true or false? False. So printf a is 0. Right? Don't divide by it. Right? So you can start to see how you can use these conditions for error checking, just like we did with our kilometer program. We checked to see how many arguments we actually got. If we didn't get what we expected, we did one thing. Otherwise, we went along with the rest of the program. Right? This is going to compile. Is it going to print anything? Nope, because it's not 0. Right? So the thing to notice here is that the first operand is a variable. The second operand is a literal. Right? It's just a number. So you can compare variables to literals. And like we did before, you can, but you shouldn't do the following. So you can, but shouldn't do the following. I'm just going to take the same statement up here, and I'm going to switch things around. Equals A. It's the same exact statement. Logically, it's the same exact statement. But read it out loud to your, or read it internally to yourself. If 0 equals A, does that sound nice? Does that sound natural? No. So that's why I'm saying that you can do this, because a computer doesn't care what's natural and what's unnatural. Right? It just cares about a bunch of zeros and ones. But you shouldn't do it because it's really bad style. Right? So it's bad style. Right? You should write code that flows and sounds like you're speaking it. Right? If A is equal to B, then print this statement. Okay? You can compare two variables. Right? And so again, the example would be A is equal to B. And then printf, both are equal. Right? Let's see. Or else printf, A and B are not equal. There we go. I'll go to the next line, even though it's not going to be true. Now, remember what we set them to? 10 and 15. Is this going to print? What is this going to print? They're not equal. Good. Right. So I can have a variable and a literal and a variable. And by the way, you can go BA, but does that sound natural? No, what do we as humans like to do? We like to organize things. And so if you've got, Husker, Fordham, I guess you could go in alphabetical order, or you'll have a natural preference, of course, for Huskers, so you'd put them first or something like that. It's all, there it gets into a gray area, because now what's your style? I don't even know where the hell Fordham is, but maybe if they're doing a CS course over there, they would put Fordham first in that example, right? All right. You can also use expressions. For example, if B times B minus 4 times A times C, and by the way, we're still seeing some people make this kind of mistake. B squared minus 4AC, if you were to write it like you said it in English, is this a valid expression in C? Nope. What do you have to do? You have to explicitly multiply things together. A, C. If that's less than 0, then I'll print a message here. What am I testing here? B squared minus 4AC. That's in the radical of the quadratic formula. If that's less than 0, then do you have real roots? Nope. So print no real roots. Can't handle that, or whatever. Right? And I don't know if it's true in this case or not. Let's go ahead and find out if it's true. Pull out your calculator and verify if you want to. Otherwise, just run the program. No real roots. Right? Because b squared, whatever it was, 10, so that's 100, minus 4 times 5 times 15. The second value is going to be more than 100, and so therefore the entire difference is going to be negative. Right? So no real roots. Okay. We mentioned that that integer of division operator, right? So, and we mentioned one of the uses of it. Check to see if A is even or odd. How can I do that? By using an expression. If A mod 2, if it's even, the remainder will be 0. And we can print out that A is even. Else, we'll print out A is odd. What was it, by the way? Was it odd? Yep. I think it was 5, right? So this should print out that it's odd. Yay, it's 5. Right? You can, but you shouldn't do the following. Sorry. You can, but shouldn't do the following. If 10 is equal to 20. You can do literals on both sides. Right? Does that make much sense? Yay. Will yay ever be executed, printed? No, 10 is never equal to 20, right? So you can do that, but you shouldn't. Why? Just take, if you want it to print yay, just take out that condition. That condition is false. That condition is called something called this is a contradiction. Something that is always false is a contradiction. Something that is always false. Right? You can, but you shouldn't, do the following. If A is equal to A, printf, yep. Should I do that? What's that? It's always true. This is a, does anybody know what those are called? Tautology, right? It is always true. Don't write code like that, okay? All right, so I will make sure that you have each one of these in the notes, this entire example. Let me go ahead and get rid of those other notes there. And again, remember that these notes are posted when I get home each night to GitHub. So, but you should be taking your own notes as we go along. Looks like we had a question online, but it was answered. Oh, yep, not a question, but yep. All right, rest in peace, Deaky. Right. The A and the command key are quickly to follow. And they don't make the butterfly keyboard on Macs anymore for a good reason. This is the third one that I've had. Right. Pitfalls. Right. You cannot use numerical comparisons for strings. Right? Just as I previously mentioned, you can't say is my name equal to Chris or something like that. I won't even show you an example here. This would end up comparing memory addresses, right? And it's not what you want. So some additional logical operators here. There's a general negation operator. Right? So any statement can be negated. That is, true becomes false and false becomes true using the negation operator. And we've already seen it. We've used it to negate the equals operation. It's just a simple exclamation point. Right? You would do this if you want to negate something. For example, what if I did this? I'll go into code mode here, and A is less than B, right? Oops, sorry, that's not gonna, there we go. Come on, there we go, there we go. A is strictly less than B. What if I were to negate that? Right. So under what conditions would this now be true? A is greater than B, is that all though? A is equal to B, right? That's the negation, right? So this is equivalent to A is greater than or equal to B. Right? Which one of those is preferable? Which one rolls off the tongue a little bit better? It is not the case that A is less than B, strictly less than B, or A is greater than or equal to B. Which one of those is better? We want to vote? Well, we don't have a consensus? The second one. Okay, I agree. That's better style. Simpler is better. There's another acronym for you. KISS. Keep it simple, stupid, right? And so the second one is simple, right? So don't overcomplicate things. It's better, the second is better style, even if they are both logically the same, right? So KISS, keep it simple, stupid. And we only have the second S so that it spells a word. If you want to leave it off and be nicer to yourself and less self-deprecating, then fine, go ahead, right? So, in general, the simpler code is easier to read. Simpler code is easier to read and thus easier to understand. Okay. We can also have what are called boolean variables. So up to now we've had integers, doubles, and characters. Some languages support boolean variables and they're called bools or boolean, right? C does not, however. C does not actually have the keywords true, nor false, nor actual boolean variables. Right? Sorry. Let me go ahead and give myself some more room here. Text. There we go. What is a boolean? A boolean variable is a type of variable that would, if it actually had it, would hold the values true or false. Right? You could set them equal to true or set them equal to false. Instead, C achieves this by reusing a variable type. C achieves this by using a simple int variable. All right. So what are true and false? 0 is false. Right? So what's true? 1 is true. But remember negation. If I negate 0, right, then maybe that becomes 1. Right? That false becomes true. But what else might become true? If 0 is the only thing that is false, then everything else must be true. Right? Generally, you can use 1 as a placeholder for true, but really any non-zero value is true. Right? So 1 is true, 2 is true, 42 is true, -5 is true, 3.15 is true, are all true in C. Right? So be careful. Make no assumptions about what value is actually true. Any non-zero value is true. Right? I could write code that made an integer variable and set it equal to 42, my favorite number, and that's what I'm going to use as my placeholder for true, and my code would still be valid. Right? If you are writing code under the assumption that my code uses 1 as true, and you're going to make it equals to 1, you're going to miss my value of 42, right? And so you need to understand that anything else is true, okay? Any non-zero value is true. But it is perfectly fine to use 0 and 1 yourself as placeholder values. You can also bring in a library. I believe it's include like a boolean, or maybe it's bool. I forget. Let's find out. Which one is it? C bool type. Bool. Bool.h maybe. If they've got an example. Oh, nope. It's std bool because it's standard. There we go. Std bool. And now what that does is that defines true, and that defines it to be 1. It defines false to be 0, the bit string 0. And so you can then use those keywords. It's all, I believe that they're all lowercase. So as an example here, you can create a bool variable, set it to true, but only if you bring in that standard Boolean library. It's perfectly fine to leave that out. It's perfectly fine to bring it in. It's your choice, player's choice. Okay? All right. So let's take a look at an example without using that library. Ignore. Come on. All right. So int is student. Right? That's going to be a Boolean variable there that I want to determine whether or not somebody is a student so that I can give them a discount or something. Right? I can set it to true. Is student is equal to 1. It would be equally valid to set it equal to 42. It would be equally valid to set it equal to -1. Right? But why get complicated? Just go ahead and go with 1. Or you can bring in that library and actually set it to true. Set it to false. Right? Is student equals 0. You can also use it in a statement. Here's my first attempt at this statement. I will eventually erase this and do it right. But if is student is 1, then I'll print f, you get free Husker tickets. Yay. Why? To preserve the sellout. They preserve the sellout by giving them away. It's sold out. Yeah, go ahead.
I don't think the equals operator and the 1 is necessary.
Good point. Right? So, KISS, keep it simple, stupid. Right? I'll call myself stupid. None of you are stupid. Right? If is student is equal to 1. Right? Why do I want to do? Well, first of all, is this even correct? What if I wanted to be different, unique, and go ahead and set it equal to 42? Would I still? That's still true. They are a student, but do they get the discount now? No, because it's not 1. So how can we solve this problem and have better style? Let's go ahead and get rid of that equals. Right? Now, just read this like in plain English. If they are a student, then we give them free Husker tickets. Right? That's the way that you should read it. Don't do equals false, equals true, or equals 1 or something like that. Keep it simple, okay? If they're not a student, no discount or a negation. How do we write that? If they are not a student, right? And note here that I prepended it with is student to distinguish it just from student. Student would be kind of like a variable that represents a student. What I want is a variable that represents whether or not they are a student, right? They are a student, true, or not a student, false. Is a good placeholder for that. Is student. And note here I'm using lower camel casing, right? So if they're not a student, then printf, pay full price tickets. Do you all still get a discount or not? No? All right. Oh, well. I'm sure that you can get them from scalpers for much less than even the student discount, right? Scalping is legal in the state of Nebraska, by the way. There are some things that you have to follow, but yes, it is legal. That's why nobody's hassling all the scalpers on game day. Right? All right, so you can perform more complex Boolean expressions as well. You can combine one or more Boolean expressions using what are called connectives. Right? What I'm talking about here are logical and logical or statements. Right? So this or that, this and that, A and B, A or C, right? Those kinds of things. In C, as with many other programming languages, the logical and operator is true if and only if both its operands are true. Right? So let's go ahead and look at, for the syntax. For syntax, use the ampersand. Now, why do we use ampersand? If I just had an ampersand in plain English, right? I don't know, Fawns and Porter, right? If you know what that is. It's a sewing show. I'm not into sewing, but it's on PBS all the time or something. You see Fawns and Porter. The and is an ampersand, right? So why do we use two of them? It's because the single ampersand already has a meaning. It's a bitwise logical operator. Don't worry about it. It's something called bit twiddling, where you can actually manipulate individual bits within a number and stuff like that. We're not going to get into it, right? Instead, just understand that we have to use two of them. If you use one of them, you will be able to compile. It'll give you no warnings, but it'll give you completely different results than what you expect. And ampersand is our logical and operator. The vast majority of programming languages use that, by the way. All right? So example, right? If I have two Boolean variables, is student and ampersand is freshman, right? When is that true? Is true if and only if what? if a person is both a student and a freshman. I guess being a freshman implies that you're a student, so it's kind of superfluous, but whatever. That's an example, right? It's false when ... When is this statement false? Is student and is freshman. It's false when at least one of the conditions is false, right? So they might not be a student, but they're still a freshman somehow, or they might be a freshman, but they're not a student. It doesn't make any sense. I don't know. They're a senior, so which means that they're a student, but they're not a freshman, so that it ends up being false. They're neither a student nor a freshman because they graduated, then it's false. Right? There are always going to be 4 conditions because each Boolean variable can be true or false, and then you can match that up with true or false. So if it's true, then the second one can be true or false. If it's false, then the second one can be true or false. There are 4 ways that this could end up. All right? The logical OR operator, operator is true if at least one of its operands is true. Right? In C, we use those pipes again. They're technically called Sheffer strokes, but we call them pipes. They're just the vertical pipes. If you look at your QWERTY keyboard, it's right under your delete button. You have to go shift and then shift /, and you get these vertical lines. Right? They're the pipes. Right? So for example, if I use the same thing as before, if they are a student or they are a freshman, that's true if either of those conditions is true. So they could be a student but a senior, and it'll be true. They could be a freshman but not a student somehow, and it'll be true. They could be both. They could be both a freshman and a student, and it would still be true. This is not like a mother telling their child that you can have cake or ice cream. What does she really mean? You can have cake or ice cream, but not both. Right? If both, this is still true. This is logical OR, not mom logic OR. Right? Yeah?
So then what would be an exclusive?
Exclusive OR would be a caret, that's bitwise exclusive OR. So you would have to just do a negation. That's it, right? Or not equals, excuse me, right? A not equals B. 1, 0, that's true. 0, 1, that's true. But if they are equal, 1, 1, or 0, 0, then yeah, all you have to do is use a not equal sign there, right? Okay. Exclusive OR would be the mother logic, where you can have cake or ice cream, but not both. And by the way, you have to eat one or the other, right? You can't go, I don't like cake or ice cream, either one, right? Or whatever. That would be false too. Your mother forces them to eat the ice cream or the cake, right? But not both. Right? It is false when both of the conditions are false. It is false only when, I'll emphasize that, only when, there we go, both of those conditions are false. You can do the comparisons with characters as well. And for this, I'll go ahead and cut and paste, right? And reformat. So again, you cannot use the equals operator for strings. You can, however, because it would be comparing the memory addresses. But you can use them for single characters. For example, if you want somebody to enter in, are you really sure that you want to delete this file? Yes or no, right? So let's actually go ahead and write that as a program here. So let me go ahead and get rid of all this. And let's go ahead and have some interactive input here. Printf, you are about to delete the entire hard drive. Are you sure? Yes, no. All right. And so we're prompting them for input here. And we're going to have to read that input from them. So I want a character here, answer. And let's go ahead and prompt them for input. We prompted them for input. We need to read the input now. Scanf. What's my placeholder for a single character? C. And answer. Is that correct? Careful. What's the compiler going to tell you? It's not correct. Why? What did you forget? The ampersand. Again, just magic for now. Okay? And for now, let's just go ahead and print it out. You entered %C, or C, and the line, and answer. All right, so it's not a full program yet, since we haven't actually deleted the hard drive if they said yes. But let's go ahead and do you want it? You're about to delete the hard drive, yes or no? Yes. Okay, you entered Y. No, you entered N. All right, so we're actually reading the input correctly now. So let's go ahead and simulate what it looks like to have deleted the hard drive. So if the answer is yes, how do I do a comparison with Y? Does that look right? No. What's going to happen here with the compiler? The compiler is going to say, I don't know what the hell you're talking about with Y. That's undeclared. Right? That's not a character Y. That's a variable named Y that I have not even declared. How do I compare it to an actual character? Single quotes. Y. Right? All right. Actually, let's go ahead and change it. So, N. No, they answered no. We asked them for a capital, right? So no. So printf, okay, your data is safe. All right. And let's go with an else statement here. Sorry. Printf. By the way, it's all bad. It shouldn't be at that indentation level. Remember, what's the tool that we used that I demonstrated to clean up your code? Remember it? All right. If not, then let's go ahead and demonstrate it again. I will intentionally make this bad. All right. Printf, deleting everything, ... Right. Oops. There. There. All right. So, oops. Cancel that. GCC. All right. So it actually compiles here. Before we actually run it and play around with it, how do I fix it? Do you remember that? A style demo.c. And ooh, nice. Much better. It's also saved as well. It's automatically saved by A style. So it formatted that. Right? All right, so let's actually go ahead and run it here. I don't need to recompile it because it was just style changes. Okay. All right, are you sure you want to delete the entire hard drive? No, I'm not. Deleting everything. What was the problem there? It's not capitalized, right? Lowercase n is not the same thing as uppercase n. Only if I put in uppercase n is it going to work. So let's be a little bit more judicious about this. Or answer is a lowercase n. We want to make sure that our data is safe here. Are you absolutely sure you want to do this? Right? GCC this again, a.out. And now, okay, your data is safe. Now, even if I go with lowercase or uppercase. Let's try that one more time. Oops, my finger slipped. H. And I also hit, without thinking, I hit enter. What's going to happen here? It's going to delete everything. Because it's neither n nor lowercase n. Is that a good design? No. So let's go ahead and go back to the original. If they said yes, I'm just changing my logic around here, right? I'm putting the unsafe thing in the affirmative. That if they put in y, or capital or lowercase, then we do the unsafe thing. Otherwise, for everything else, we do the safe thing, right? And now, it doesn't matter. Oops, sorry. GCC it. Run it again. Now it doesn't matter if I sit here and mash the keyboard, right? And your data is still safe. Much, much better design there, right? So think about your logic. Think about how you can reformulate your logic to make your code safer and better style and things like that. All right, I'll put that in the notes. All right, in our last few minutes here, let's consider the following pitfalls. All right, so look at that code there. What is my intention? What is my meaning? It's clear from what I tried to write here, is that if the value of a is anywhere in the range from 0 up to 10, inclusive on both ends. So if it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Then we execute whatever code is in here, okay? Let's test it out. Let's test it out and see what we actually get over here. Right? I'm going to go ahead and get rid of this. And of course, I need a here. Int a is equal to 10. Now, I will printf a is in range, 0 to 10. There we go. All right. So when I compile this, I don't know if it's going to... Okay, good. It's fine. The compiler says, yeah, that looks good. Right? All right, fine. Let's go ahead and run it. What's it going to output? That it's in range, okay. Let's go with something right in the middle, 5. What's it going to output? That it's in range. Okay, fine. Let's go with something at the other end. All right. And let's go ahead and run that, and we should expect it to be fine, right? A is in range, okay. We're good. So, ship it. All right. What did I fail to test? Yeah, test other extremes outside the boundaries. What about negative 10? Should it print anything? Okay, so let's test it. Huh, in range. No, exactly, no. And in that tone. That's the correct tone to do it with, right? It's 100. Should it output anything? Still outputs true at 100. So what's going on here? Oops, that's not what I wanted. Sorry. So the above code will compile. Above code will compile. It will run, but it will not be correct, right? What you expect, right? It is correct from the computer's perspective. You tell a dumb computer to do something, and it does exactly what you told it. You tell it to delete the hard drive, and as long as you answer yes, it will delete the hard drive, right? It only does what it's told. What is going on here? The correct way would be what? Split those two statements up. If 0 is less than or equal to a, and a is less than or equal to 10, then we do whatever we're trying to do. Let me walk you through what this is doing, right? With an actual particular example. Let's go with negative 10. So it evaluates left to right. So let's do what the computer does, because it's exactly what we told it to do. Is a less than or equal to 10? Is 0 less than or equal to a? Remember, a here is negative 10. Is that true or false? False. What is false? 0. So it becomes 0. Now, is 0 or less than or equal to 10? Yeah, right? This is a consequence of not having Boolean variables. And using the Boolean library still doesn't save you from something like this. The only thing to save you from something like this is, first of all, writing correct code. But here's another thing that can save you from this. Hopefully, I'm crossing my fingers here to see if it actually works. Wall demo. Oh, cool. It's giving me warnings now. The comparison of a constant 10 with Boolean expression is... Oh, sorry. Did I screw this up? Nope. Yep, nope, this is correct. Is always true. Remember, this first one evaluates to 0, right, under that condition. 0 is less than or equal to 10. That's always true. Comparisons like this do not have their mathematical meaning. Very, very nice compiler warning here, right? It would have been really nice. It would have been even better if it told me that in the first place, but it didn't, right? What I just did is I used GCC as what's called a linter. So what's lint in the real world? Not in the competing world. I don't have any lint on me right now. But t-shirt lint, who cares? Right? What's lint? It's little pieces of fabric, right? That are left over from the dryer. So it's kind of it's not dirty because your shirt is clean. It's just some lint left over. So it's not dirty code. It's not erroneous code, but there's junk on it, right? You want to get rid of it. You want to delint it. Right? So that's what warnings are. Warnings are looking at your code and looking for lint in your code. Things that that's not going to cause a huge problem, maybe, right? Because it's not dirty, but you probably want to take a second look at that and see if that's actually what you mean, right? Is this actually what we mean here? Certainly not. So, how do I make GCC into a linter? By telling it to turn on all the warnings. And this is how the grader works too. So if you ever see a warning on the grader, make sure you address it, because probably one, you're doing something wrong. And two, it's worth points. If we still see a bunch of warnings on there, then that's bad design, right? How do you tell whether or not there is lint or potential issues in your code? You turn on warnings. That's what the -W flag is, right? The all, it's not wall like the wall over there and holding up the ceiling. It is warnings. Turn them all on, right? And when you do that, a whole bunch of problems that you might have seen before come to light. For example, not having an ampersand there, right? That's a standard warning. Now it's a standard warning. It's not necessarily a standard warning on all systems, right? But using the wall flag turns your compiler into a linter. It's something called static analysis, and you can get really deep into static analysis. In fact, later on, I'll show you, if you want to take a look at the troubleshooting guide on the GitHub repo, I walk you through a couple of different options for using static analysis. Static analysis is simply just a program looking at your program and finding potential problems before you compile it, right? So you can find things like this. We expect you to use the WAll flag because it's easy. We're not going to expect you to use those other tools. In fact, some of those tools, none that you have access to, but some of those tools can cost thousands or millions of dollars for professional auditors to come in, run their tools to find potential issues and security flaws in your code. Right? And so you're hiring an outside firm to do a full static analysis using their high proprietary tools, and they charge because they built them and they want to make money off of them, and they're millions of dollars or whatever. But there are plenty of free tools out there, right? And you're not writing any critical code like that. Okay. Maybe one more pitfall. Pitfall 2. You tell me what's wrong with this code. Stare really, really hard at it. Int a is equal to 5. Yeah, go ahead.
It's not equal to equals.
Yeah, I forgot one of those equal signs. So it looks like, but if you don't sit there and stare at it, right, even a seasoned programmer can miss this, right? So let's go ahead and find out what the consequence of something like this is, right? So int a is equal to 5. If by the way, here I violated that style tip that I gave you. That's one instance in which I'd say it's better to use this because you're keeping it as like a range. So that's perfectly fine to violate that style. I'm putting the variable after the literal. You could put a is greater than or equal to 0 and a is less than or equal to 10, but that doesn't roll off the tongue as nice, right? And it looks weird. Anyway, let's go back over here and look at the second pitfall. So if a is equal to 5, then a is 5. All right. And I'm going to go ahead and GCC it normally. No warnings. Okay. I must be doing everything correctly, right? Let's go ahead and find out if this runs. Oh, it's 5. Ship it. It works. What happens when it's not 5? It is 5. No, it's not. It was 10. Right? Yeah, now it's 5 again. What is the single equal sign again? It's the assignment operator. So what this is doing is saying assign 5 to the value a. And it simplifies to this. What value does a have now? 5. 5 is true, and therefore that's why it executes. Right? All right, well, let's back this up. And do I have lint on my t-shirt? On my fine dress t-shirt? Let's find out. Suggest parentheses around assignment as a truth value, right? That doesn't look right. Warning. Okay, take a second look. And it's not understanding that my intention was to actually check to see if it's equal. It's thinking, oh, you must really mean that you want to assign it. Well, here's a better way of doing that by surrounding it with parentheses, right? So using a linter here will catch a lot of these things. W all flag. And I believe that you can go either way here. Maybe not with Ubuntu, but let's find out. Yeah, you can put it before or after, it doesn't matter. A lot of people are still having trouble with the LM flag. Again, I don't think you need the LM flag at all on CS50. It's just some systems if you've jumped ahead to hack 2. Okay. All right, any questions? So you've got your hack 2 tomorrow. Then you've got your lab immediately when we come back. Otherwise, enjoy the 3-day weekend and the 40-point spread.